Hi there and welcome to my science tutorial again. In this video, we are looking at Lewis acids and bases. If you haven't seen our introductory videos and other videos on acid and bases, check the description of this video and click on the links to access those videos. Alright, so let's get started. So what is Lewis acid and Lewis base? It is very simple. Lewis acids are electron pair acceptors. So acids, they are electron pair acceptors. And then the bases, they are electron pair donors. All right. So this is the basic definition of an acid and a base. Lewis came with the concept that any species that is able to accept a lone pair of electron is an acid, and then the base is what is donating that particular electron. So what we have to take note of is that all Bronsted-Lowry acids and bases are also called Lewis acids and bases. So you'll find out that Lewis concept is a much wider definition of an acid and base compared to Bronsted. Okay, you'll see that very soon in some examples that we'll look at. So let's look at this illustration. Let's look at B with a lone pair on it. So there's a lone pair on B. As a result of that, it's going to have a negative charge. Okay. Now let's look at a proton, H plus. Now what is going to happen? You end up having B bonded to H. Now the question is, how is that going to happen? Now this is what happens. The proton here, hydrogen plus, has no electron, yet it has an s orbital which can take a lone pair of electron. So this species here, B, has an extra lone pair which it will donate into the empty orbitals of proton and then form a BH. So in this case, the B is a proton donor. So we'll call it the Lewis base. Lewis base. And what is accepting the electron? It is the proton. So we'll call it the Lewis acid. All right. Now, what results from the donation of electron from a Lewis base to an acid? Now, the kind of bond that this results in is called coordinate covalent bond. Now, it is also known as dative. It is also known as dative covalent bond. Okay. Dative because one guy is donating everything while the other one is just receiving. So we call it a dative covalent bond. Now let's look at some example. Let's take a proton again and water molecule. So this is our proton H plus and water. Remember the shape of water is V and it has two lone pairs on the oxygen. So this species here, proton, lacks electron. That means it has an empty orbital, so it will be able to accept a lone pair of electron from the oxygen. And that is exactly what is going to happen. The arrow moves from where the electron is to where the electron is not. So the oxygen is donating a pair of electron into the empty orbital of the proton. Okay, so the result of this is that we are going to have oxygen bonded to three hydrogens this time and a lone pair on it. Okay, by this time it's going to carry a positive charge. because it's becoming more electropositive. All right. So let's look at another example. Another example is ammonia, NH3, donating a proton. Remember ammonia, the nitrogen has a lone pair on it, okay? So what is going to happen is it will donate this lone pair into an empty orbital of hydrogen or proton, okay? So this is going to result in a dative covalent bond where we have N bonded to four hydrogens. By this time, it is going to have a positive charge on it. So again, the ammonia, the electron is our base, and the proton accepting the electron is the acid, according to Lewis. Over here, water is the base, and this is the acid. So let's look at another example. When you take ammonia and trifluoroborane, NH3, we have a lone pair on the nitrogen, and then we have boron bonded to three fluorine atoms. Now, this time, the boron over here is not carrying a positive charge. However, it has an empty orbital. So the ammonia is able to donate the electron into the empty orbital of boron. So as a result of that, we're going to be having nitrogen in a coordinate covalent bond with boron, which is bonded to three fluorine, and the nitrogen itself bonded to three hydrogens. Okay, so in this case, what is the acid? The acid is the electron, is a electron acceptor, which is the boron trifluoroborane. So this is the acid, and this is a base because it is donating the electron. Okay, so this is very simple. It is very simple. With a boron here, you can tell that it has an empty orbital when you look at its hybridization. You'll find out that it has an empty orbital which can accept a lone pair of electron. So let's look at how do you identify Lewis acids and bases? How do you identify Lewis acids and bases? Now, based on the definitions, when we take Lewis acids, some common source of Lewis acids could be number one, we can talk about proton, of course, proton, hydrogen plus. Hydrogen plus, hydrogen has s orbital, and when it loses its one electron, it becomes plus, where the s orbital becomes empty, so it has the ability to accept a pair of electrons. Now we can also talk about cations. All cations. Cations originates from the loss of electron. So if it is able to lose electron, that means it also would have the ability to accept electrons. Okay. So cations, especially transition metals, are Lewis acids. So we can talk about copper 2 plus. Copper 2 plus can talk about manganese 2 plus, Mn 2 plus. You can talk about iron, Fe 3 plus, Fe 2 plus. You can talk about titanium 4 plus. You can talk about vanadium 5 plus. So all these are transition metals, and the unique thing about transition metals is the fact that they have a d orbital, and the d orbital is capable of accepting 10 electrons. And usually the d orbital is not fully filled, so they have a lot of empty spaces in there to accept pairs of electrons. So with this, we can say that this is a Lewis acid. So you realize that when it comes to Bronsted and Lowry concepts, they don't account for these metal ions. Okay. Now another group of Lewis acid could be complex ions with empty orbitals. So we can talk about complex ions with empty orbitals. Okay, so we take something like PTCl for 2 minus. So the platinum here has a lot of empty spaces in there, which will allow it to form a coordinate covalent bond. Now you can also talk about molecules with empty orbitals. Of course, there are many molecules with empty orbitals. So molecules, molecules with empty orbitals, you can, let's say BX3, ALX3, you can talk about BEX3. So in this case, the S can be, it can be a proton, hydrogen, or the halogen ClF, iodine. All any of these species could fit in for X, okay? And then the central atom, which is boron, aluminium, this is Al, beryllium, all these ones are capable of having empty orbitals, okay? Now, what about Lewis bases? Lewis bases, we can only mention some of them. We can talk about water, H2O, SO2, SO3, NH3. We can talk about amines, yeah. So R bonded to NH2. These are amines. So in this particular formula, the nitrogen has a lone pair on it, and the R is an alkyl group. Okay. So for example, we can talk about metallamine. Metallamine is CH3 and H2. Now we can talk about alkanols. Alkanols are like alcohols. So we're represented by R bonded to OH, okay? The oxygen is the one having the lone pair of electron. Now we can also talk about all single atoms with a negative charge. So single atoms with a negative charge. Good. So these are some examples of Lewis acids and bases. I hope this video comes in handy and is helpful. If that is the case, remember to like this video and also subscribe. Thank you.